Welcome to Lecture 2.1, Propositions and Logical Operators. In logic, a proposition is a sentence to which one and only one of the terms true or false can be applied. This is a little bit unfortunate because outside of logic, the term proposition usually refers to a true statement, sort of like how we use theorem, but usually proposition is not quite as grandiose. Let's do some examples of propositions in logic. 4 is even. That is true. 4 is in the set containing 1, 3, and 5. That is false. 2 plus 2 is 5. That is false. There is intelligent life on other planets. We may not know the answer, but it is definitely something that is either true or either false. Or at least we think. Maybe there's some other alien pseudo-life form like viruses that we can't decide whether or not it's true or false. But the point is that just because we don't know the answer doesn't mean it's not a proposition. And finally, this one is a little bit controversial. The following computer program halts. So I'm going to put a question mark here because this is kind of like the last one. It's either true or false. We don't necessarily know which one it is, but there's a big theorem in logic that says that there is no algorithm to determine this. So this is something which you and I would probably say is either true or either false, but it may not be provably true within the laws of logic. So this is something that perhaps a logician would say technically this is neither true nor false, so it is not a proposition. We will revisit this in a later lecture when we actually will prove why a statement like this is in general unprovable. Let's do some non-examples of propositions now. First, do you understand this concept? That might be true for some people and false for others, but it is not a statement which is inherently true or false. Watch the rest of this video. That is a command. It is not a statement which is true or false. X squared equals 2x minus 3. This is true for some values of x and false for others. So this is not a proposition. We could make it into a proposition, though, by adding a few words. Say, by adding for all x or for some x. Next, this statement is false. This looks like it's different from the first three on the surface because it seems like something that should be true or false. But if we dig in a little deeper, we see that neither the assignment of true nor false makes sense. So if this statement is true, then by definition, this statement is false, is also false. So it's true and false. However, if we conclude that this statement is indeed false, then it has to be true. This is something called a paradox. It is very closely related to Russell's paradox, which we briefly discussed in an earlier lecture, and we will get into later in more detail because it is closely related to the impossibility of the halting problem, which I mentioned above here. And finally, Schrödinger's cat is dead. This example, of course, is from quantum physics. If you have never heard it before, it probably doesn't make any sense. And that's fine. I would recommend taking a minute or two to Google it because it is a fun little fact. Basically, you put a cat in a box and then you randomly decide whether to decay an isotope or not. I think that's what happens. And basically, there's a 50-50 chance that it decays and the cat dies. And if it doesn't decay, the cat lives. And the basic idea is that the cat, until you open the box and look at it, it is somehow this superposition of both being alive and dead at the same time. I know, it makes no sense. Quantum mechanics is a very strange subject indeed. But apparently a lot of it, if not all of it, is true. Okay, so look that one up if you don't know of it. But it's definitely an example of a proposition, of a non-example of a proposition, because it is neither true nor false. In algebra, which we're all familiar with, variables are placeholders for numbers, which we often denote with letters like X, Y, and Z. We can use other letters too, but those are the most common. In logic, we can also have logical variables. We usually use symbols such as P, Q, and R, and instead of being placeholders for numbers, they are placeholders for propositions. Logical variables can take the values of 0 or 1, which denote false and true, respectively. Compare this to regular variables in algebra, which, as being placeholders for numbers, can take the value of, typically, some real number. Or if we want to allow it, maybe a complex number as well. We can combine simple statements into compound ones using words and phrases such as and, or, not, if then, if and only if, and so on. Except for not, which acts on a single proposition, all of these operations listed above act on pairs of propositions. We will precisely define each of these and introduce standard notation. We will use the concept of a truth table for each one. This describes the effect of the logical operation on all possible inputs. To begin, if P and Q are propositions, then their conjunction, sometimes written P and Q, sometimes the and is capitalized. It can be denoted with this little wedge symbol, P and Q, is defined by the following truth table. So hopefully the truth table is self-explanatory. We have a column for all possible inputs, P and Q. So there are clearly 4 inputs, 0, 0, 0, 1, 1, 0, and 1, 1. And this order is not necessarily standardized, but I'll stick with it throughout. And then the last column is the output. So notice that the output is 1 if and only if both P and Q take a value of 1, hence the name AND. The next, of course, is the logical OR function. If P and Q are propositions, then their disjunction, sometimes written P or Q, and denoted with this upside down wedge, is defined by the following truth table. So now the output is 1 if either P or Q is equal to 1, or both. Next, if P is a proposition, its negation, sometimes written not P, sometimes the not is capitalized, or denoted with this negation symbol in front of the P, as defined by the following truth table. If P is 0, not P is 1, and if P is 1, not P is 0. Sometimes the negation of P is instead denoted with a bar on top of P, or even a tilde in front of P. And I think this choice of a tilde is used a lot if you're sending an email, because this negation symbol is not a standard character found on your keyboard, and the overline, while it's probably possible to do that, is not standard formatting. Our next operation is a little less common colloquially than and or not. And to motivate it, consider the following statements. I am going to wear my raincoat if it rains. If I do not pass this class, I will not graduate. And finally, I will be on time for this class provided my car starts. Though these are phrased quite differently, all of them can be written in the form if some condition, then some conclusion. Which brings us to the following definition. The conditional statement, if P then Q, denoted P right arrow Q, is defined by the following truth table. And a few of these entries you may find surprising or counterintuitive. Now, first of all, instead of saying if P then Q, I will often say P implies Q. And if I just leave it like that, I'm assuming that P implies Q is true. So here, if P is false and Q is true, then P indeed implies Q, or P implies Q is true. If P is false and Q is true, then P also implies Q, which is perhaps surprising, because why should a false statement imply a true statement or a false statement? Why should that be true? More on this shortly. Not surprisingly, if P is true and Q is false, then P certainly does not imply Q. So P implies Q is 0. And finally, if P is true and Q is true, then P implies Q. So this entry is 1. So notice that another way to write this is that the output is 1 if P is false or if Q is true. So equivalently, not P or Q gives the same output. So if P is false, then those two entries are 1, and if Q is true, we get 1 here, and then we get 0 there. So these are said to be equivalent propositions, and more on this later. But what I want to turn to now is, why should these two entries be 1? It hopefully makes sense why the third and fourth entries are 0 and 1. But why should P imply Q whenever P is false? The answer is to think of a conditional statement as a guarantee. In other words, P implies Q asks whether that guarantee was kept. This is best seen with an example. So let's do one now. Suppose I make the guarantee that if you get at least 90 points on the final exam, then you will get an A in the class, no matter what. So here, P is the statement that you get at least 90 on the final exam. Q is the statement you get an A in the class. Let's check all 4 possible pairs of P and Q to verify that this truth table makes sense. So, case 1, this first row. So let me pick a better pen color. So case 1 is when P equals 0 and Q equals 0. So here you get less than 90 on the exam, and you do not get an A in the class because Q is 0. So you don't get an A. So let me ask you, was this guarantee kept? Sure, I did not violate this promise. So yes, this checks out. The second example, or the second row in the truth table, this one right here, P equals 0, Q equals 1. Here, you get less than 90 on the exam, but for some reason, you get an A. You know, maybe you got an 89 on the exam, and maybe you had a really high homework score. Did I break my promise? No. So you did not satisfy this condition, but you still got an A in the class. Nothing about my guarantee was broken. So if this guarantee is on my syllabus, I did not break the rules of my syllabus. So that checks out. And that's why this entry up here is 1. So next, the third line is when P equals 1 and Q equals 0. Here, you get at least 90 on the exam. But since Q is 0, you do not get an A in the class. You don't get an A. Here, I broke my promise. You satisfied this condition. You did not meet this conclusion. So there, I broke my promise, and that's why this entry is a 0. Finally, the last case is when P equals 1 and Q equals 1. Here, you get at least 90 on the exam, and you get an A in the class. There, I kept my promise, and that's why this last entry is 1. Finally, let's note that what I said in the previous slide still holds, that this is equivalent to not P or Q. Now, the formal notion of equivalence we will discuss in a later lecture. But for now, notice that I kept my promise, or at least I did not break my promise, if P is false or Q is true. So if you got less than a 90% on the final exam, then this policy did not go into play, so I did not do anything wrong. Or if you get an A in the class, in which case I did not break this promise either. The only time that I broke the promise is when you got an A, when you got at least 90 and you did not get an A in the class. That's just this one row right here. It should come as no surprise that the order of the condition and conclusion in a conditional proposition matters, which brings us to the following definitions. Given a proposition, P implies Q, the converse is the proposition Q implies P. The contrapositive is the proposition not Q implies not P. The inverse is the proposition not P implies not Q. And the negation of P implies Q is what you get when you just stick a negation symbol in front of it. So it's not quantity P implies Q. Let's make a few remarks now. A conditional proposition is not equivalent to its converse, inverse, or negation, but it is equivalent to its contrapositive. This is something that I want to verify with the truth tables. So here are the input columns for P and Q. And here are the other 5 columns corresponding to the proposition and its converse, inverse, negation, and contrapositive. Let's go through these one by one. So first of all, P implies Q. That is the original statement. We know that that is not P or Q. Next is the converse, Q implies P. So that is not Q or P. So P is false in the first and the third rows. Sorry, Q is false, and then P is true in the also in the fourth row. So that's where we get 1, 0, 1, 1. And notice that that's the same as the regular statement, except for these middle 2 entries are flipped. And that's due to the inherent asymmetry of P implies Q versus Q implies P. Okay, now we have the contrapositive. So let me use blue for that, matching the color combination of here. And maybe let me add converse. I'll write it as well, and then I will write contrapositive. And the contrapositive, so is not Q implies not P. So using this notation, the or, that is not this first term, which is not Q, or the second term, which is not P. So this is Q or not P. If you want to see that in more detail, that's not Q or not P. So it's easy to see that Q is true in the second and the fourth row, and then P is additionally false in the first and the second, so we actually get the same as we do for the original statement. So the contrapositive is equivalent to the original proposition, and that's this second line right here. Okay, now we have the inverse. Not P implies not Q. Let me switch back to red. And so this is, again, it is not this first term, so not P is P, or not Q, the second term, not Q. And one thing you can note is that is the contrapositive of the converse. And we just showed that a statement is equivalent to its contrapositive, and by equivalent I mean it has the same truth table. So the converse has to have the same truth table as the inverse. We can also check that P is true in these last two rows, and then not Q is true additionally in this first row. Okay, finally, we have the negation. Let me write that up in green. Sorry, my pen green is a little bit different than the green that are on these slides. And so the negation is just the opposite of P implies Q. So we take these entries 1, 1, 0, 1, and we just flip them. So we get 0, 0, 1, 0. So this is different from all of the others. So now you can see my color coding scheme. Up here, converse and inverse, I both used red because I knew that they were going to end up being equivalent. Contrapositive is different from both of these, and then the negation is different from all three of those. Okay, so now that we've verified this with a truth table, let's go back to our familiar example from earlier and take these four operations of that example, namely the one about getting a 90% on the exam, guaranteeing an A in the class. Here is that example. My guarantee is that if you get at least 90 on the final exam, you will get an A in the class. So P is the statement you get at least 90 on the final, and Q is the statement that you get an A in the class. Here is an abridged version of the truth table from the previous slide. So let's consider, first of all, the converse and the contrapositive, because these are a lot more common than the inverse and the negation. So let's just do these two. I think I'll add those two as well. But let's do the converse first. So the converse is, let's write that down. The converse is Q implies P. And this says, if you get an A in the class. Now it's a little bit weird when we are dealing with future tense. So if you get an A in the class, so I'm going to massage my grammar so it actually makes sense. So if you get an A in the class, then you got, so it's, again, no, it's past tense even though I'm speaking about something hypothetically in the future. I really don't understand why this works grammatically, but I just speak English. I'm sorry if you're not a native English speaker, I don't have a better answer. So if you get an A in the class, then you got an A on the final exam. So that's the converse, and that is certainly not equivalent to the original statement. Next, let's do the contrapositive. So contrapositive. So this is not Q implies not P. And this says, so if Q is false, that means if you didn't get an A in the class, then you got below 90 on the final. That is equivalent to the original statement. And notice that the original statement, these two entries that we were a little bit unsure about whether they should be there, because why does false imply true? If they were not there, then this would not be equivalent to the contrapositive. Okay, so next let's do the inverse. So the inverse is equivalent to the converse. So this is not P implies not Q. And this says if you get below 90 on the final, you will not get an A in the class. Which sounds a lot different than the converse, but we've already shown that they are logically equivalent. And finally, let's do the negation. So notice that I have figured out how to do a custom green color that is more legible than the default. So the negation is not P implies Q. And before we try to write out what this is in a sentence, let's do it in the truth table. So not P implies Q is the opposite of P implies Q. So that is 0, 0, 1, 0. And notice that that is true only when P is true and Q is false. So that is P and not Q. Okay, so let's try to understand what this really means. So it's tempting to say that this is true when, well, let's see, so it's only true when P is true and Q is false. So does that mean that if you get an A in the final exam and you don't get it, or if you get a 90 in the final exam, that you don't get an A in the class? Well, that's actually not equivalent. So what I just said, if you get a 90 in the final exam, you don't get an A in the class, is P implies not Q. I'm running out of room here, but let me write down what that is in terms of the truth table. That is not P or not Q, and that is true unless P and Q are both 1. So that is actually 0. Sorry, I'm running out of room here. 1, 1, 1. That, in particular, can't be the same because anything implies anything is going to have 3 out of 4 ones, and this only has 1 out of 4 ones. Okay, so what is this saying? This is saying, so this checks out only when I've broken my promise. So the negation of this, it's not maybe a great way to say it, but so this is saying this holds when I've broken, oops, let me spell that better, when I've broken my promise of 90 implies an A from the from the syllabus. So again, in all of the other cases, I may or may not have broken my promise, but so that's what this is checking out is it's returning true when I have absolutely broken my promise. Our next operation is the biconditional statement P if and only if Q, which is denoted with a double arrow, so P double arrow Q. This is true precisely when P and Q have the same truth values. Let's see what this looks like on the truth table. So here are the inputs, P and Q. P implies Q. We know what that truth table looks like. The converse, Q implies P, that's slightly different. The contrapositive, not Q implies not P, same as the original statement. But now we have P if and only if Q, and that's true precisely when P and Q have the same truth values. In other words, they are both false or they are both true. This is definitely different from anything we've seen so far because it's the only operation where there are 2 zeros and 2 ones in the truth table. All of the others, the or statement, the and statement, the conditional operator, and the converse and the negation and the inverse and all those had 3 ones and 1 zero or vice versa. Okay, finally I should mention that it is common to abbreviate if and only if when we write it as IFF. So we don't, since this phonetically would sound the same as IF, even if we write it like this, we say if and only if. Let's conclude this lecture by comparing 3 things that we unfortunately often say interchangeably incorrectly. So those are if, only if, and only if. So consider the following 3 statements. I wear orange if it is Friday. This is a tradition at my university, wearing orange on a Friday. The second statement is I wear orange only if it is Friday. And the third statement is I wear orange if and only if it is Friday. Before we get started, let's think about what people mean when they say these. So I wear orange if it is Friday. So this is saying if it is Friday, I'm going to be wearing orange. And every single Friday I will be wearing orange. It's not saying anything about what I wear on Thursday. I might be wearing orange on Thursday. I might be wearing it every day. The second statement, though, is different. It says, I wear orange only if it is Friday. It's saying, you won't catch me dead wearing orange on any other day of the week. I may never wear it on Friday, but the only possibility of me wearing orange is Friday. And finally, this is saying, sort of both of those put together, I wear orange if it is Friday and only if it is Friday. So I wear it on a Friday and I will only be wearing, and I will never be wearing it on any other day. So in other words, this is saying I wear orange every Friday without fail. Now we have all probably misspoken these things in colloquial language. Okay, so let's summarize what I just said, and let's try to explain it a little bit further. To begin, the first one, if it is Friday, then I wear orange. That is a way to rephrase this first statement with an if condition, then conclusion. In terms of the notation that we've learned in this lecture, if Friday, then orange, or Friday implies wearing orange. Another way of saying it is, being a Friday is sufficient for me to wear orange. Note the word sufficient. Equivalently, if I am not wearing orange, then it is not Friday. That is the contrapositive of this statement. In other words, if I am not wearing orange, that's the negation of this, then it is not Friday, the negation of the first statement. So equivalently, not orange implies not Friday. Let's do this for the second one now. I wear orange only if it is Friday. So this is saying, you won't catch me dead wearing orange on another day, but if I'm wearing orange, you can guarantee that it is Friday. So if I am wearing orange, then it is Friday. In other words, orange implies Friday. That is the converse of this statement. So let's take the contrapositive of this. If it is not Friday, then I am not wearing orange. So being Friday is necessary for me to wear orange. If it is not Friday, then I am not wearing orange. Or symbolically, not Friday implies not orange. Let's now summarize what we just learned, comparing conditional to biconditional statements. So the following things are equivalent to if P, then Q. P implies Q. Q follows from P. P is true only if Q is true. Now this one is maybe not quite so obvious that it's equivalent to these two. So I encourage you at any time when I show you one of these to pause the lecture video and convince yourself of why it is equivalent before moving on. Now notice that if I had said P is true if Q is true, then that is actually the converse of this. P implies Q, P if Q. And so only if is actually the converse. You can think of it like the converse of the converse. Okay, so moving on. Q is true if P. That one I think is a little bit more intuitive than the previous one, but maybe a little bit harder than, say, the first two. Next, P is sufficient for Q to be true. And finally, Q is necessary for P. So by the time you get down to these last two, it's so hard to keep track of all of them. I encourage you to look at my slides and compare all of these to that example of if it is Friday, then I wear orange. Okay, so that's a list of things that are equivalent to if P, then Q. And next, things that are equivalent to the converse, if Q, then P. So some of these really are the true converse. So P implies Q, the converse is Q implies P. And then other ones all of these you actually get from just reversing the roles of P and Q. So I will call that the converse, even though the converse we defined for an if-then statement like this or that, not for a single statement like Q is necessary for P, even though this is equivalent to an if-then statement like this. So I'll say that the converse of Q being necessary for P is necessary for Q, and the converse of P is sufficient for Q is sufficient for P. So these things all match up like this. The converse of P follows from Q is Q follows from P. And remember how I said that maybe you disagree with me, but for me the least intuitive one on this list is P only if Q. Well, one way to see it is take the converse of that, and we get Q only if P. And then as we saw in the previous slide, if we switch only if to if, that's the same thing as basically taking the converse there. So here we are so if we take the converse twice, we get two things that are equivalent. And for me, this one was more intuitive than that one. Okay, let's conclude with comparing these to the biconditional operator. The following statements are all equivalent to, here is a list of things that are equivalent to the statement P if and only if Q. First, P is necessary and sufficient for Q. So P is sufficient for Q and P is necessary for Q. The first one says that if P, then Q, and then if Q, then P. Next, P is equivalent to Q. Next, if P, then Q, and if Q, then P. And finally, because this third one is a little bit clunky, we can instead say if P then Q, and conversely. So the conversely takes care of the if Q, then P. Okay, before signing off, I want to make one comment about an unfortunate bad habit of a lot of mathematicians, probably myself included. It's pretty much universal that when people define things mathematically, they really should be saying if and only if, but they usually just say if, and it's completely understood what they mean. So for example, let me give you a definition, something that you know. So an integer n is a perfect square if n equals k squared for some integer k. All right? So you read this and you know exactly what it means. Well, this if really should be if and only if. Because think about what this is saying. This is saying if n equals k squared, then n is a perfect square. It's not saying that, oh, maybe there's other perfect squares that don't satisfy this. But it's completely understood from the context that this if and only if should be there. This is just one of many things that mathematicians do sloppily and incorrectly, but they get away with it because, I don't know, they can. One of my favorite examples, a slight tangent, this won't take long, is we all know that sine of x squared, we usually write as sine squared of x, right? But sine of x 1 over that is not equal to sine negative 1 of x, because that is usually shorthand for arcsine of x. So try convincing freshman calculus students that, well, for short, the exponent goes up here, except in the case when it's equal to negative 1, in which case it means something completely different. Okay, rant over, and I think we're going to leave it there. See you next time.